Welcome back, folks. In this video, we'll be talking about acceleration, what it is, we'll define it, look at a formula for acceleration, and then solve some problems that pertain to acceleration. Okay, so first of all, what is acceleration? Acceleration is just a speeding up, slowing down, or a change of direction. You've experienced all of these things. Change in direction. If you're sitting on the bus and or in a car and you go around a corner too fast, you feel like the car is pushing on your body. Well, that's because that's exactly what it's doing, and it's helping you to change direction. And really, all three of these things, what it means is that you are experiencing a change in velocity. Okay, so if you change your speed, which is the number part of velocity, or if you change the direction of your motion, you're changing your velocity, and if that's the case, you are accelerating. So defined with words, we call acceleration, we define it as the rate of change of velocity. Rate of change of velocity. Okay, and we've experienced rate before. When we talk about rate of change of position, we talk about velocity, or we talk about rate of change of speed, or distance, we talk about speed. Rate of change just means something, the change in velocity divided by time. Okay, so acceleration, which from now on I'm just going to write it as ACC''N. Acceleration is a vector, which is important because it does have direction. Okay, the other thing to keep in mind here, and we'll touch on this more as we go through a unit, but the acceleration of an object can be found by looking at the slope of a velocity time graph. Slope of a velocity, slope of velocity time graph. Okay, so I'll show what that looks like here in a minute. Okay, so formula that we'll use for acceleration, and this is on your formula sheet. A is equal to delta V over time. That is the Greek letter delta. Delta just means change in. Change in. Okay, so it's the change in velocity divided by change in time. Now, how we find the change in something, we look at its final velocity minus the initial velocity. We divide it by time. Okay, so we'll define what all of these variables are. First of all, A, that just is acceleration. And I'll come back to the units for acceleration in a minute. VF is final velocity. Okay, so we talked about acceleration as being a change in velocity. Well, VF is just the final velocity. VI is the initial velocity. Okay, and then of course time on the bottom is t. Okay, and we generally talk about that in seconds. Okay, I should put velocity, that's in meters per second. Those are our units that we use to talk about velocity. So acceleration then, if we look at the units in the formula, if our change in velocity is in meters per second divided by time in seconds, these are like the units for acceleration. Okay, so it's meters per second per second. Another way that we talk about that is meters per second squared. Okay, so acceleration have units of meters per second squared. Okay, so just to quickly touch on this graph, which is velocity versus time for an object. So this is saying that, hey, after 1 second, an object has a certain velocity, and then at some later time, the velocity is going to increase as time goes on. So if we were to draw a nice straight line through that, yeah, that's not bad. Okay, so if we were going to find the slope of this line, and this will just be a very quick and easy diagram to look at. This rise would be a 7.5 meters per second because our y scale is now in velocity. So this thing has changed its velocity by 7.5 meters per second in a time of, this run would be 3.75 seconds. Okay, so if we go and find that slope, its rise, 7.5 meters per second divided by the run. Okay, and we divide those out, we find that the acceleration of this object will be 2 meters per second squared. Okay, and again, we'll come back to that in more detail. Okay, sliding down a little bit here, we'll look at gravity. First of all, we'll mention gravity. We will, again, come back to this in more detail. Gravity is a special number for us. if any object is flying through the air or being dropped off of a building, gravity close to the surface of the Earth is 9.8 meters per second squared downward. Down. Okay, another way that we commonly write that is we will talk about our upward direction as being positive. So we would often use that numerically as negative 9.8 meters per second squared. Okay. On the right-hand side, we have some different examples of looking at velocity and acceleration for some different situations. So if a car sitting at a stoplight hits the gas, well, this velocity, we're going to assume that it's moving in the positive direction. So if it's moving in the positive direction, it will have positive velocity. And if something is speeding up, its velocity will be increasing. Okay, so that thing will be getting faster. Okay, so next, if we have from rest, you back out of your driveway, you slam that gas, you're going to speed up in the negative direction. Okay, so if a plane lands and comes to a stop, so that velocity would be moving in the positive direction, but it would be slowing down. So, it would be slowing down, so the acceleration of this object would be negative. Okay, if you drop a rock off a cliff, it would move downwards. It would have negative velocity, but it would also be speeding up in the negative direction. So acceleration would be negative as well. Okay. However, if you throw a rock straight up, if we could think of that direction as being positive, but it would be slowing down. Eventually, we'll talk about projectiles or things traveling through the air in more detail. But eventually, when you throw a rock straight up for a tiny moment in time, it will stop before it starts coming back down. Okay, so for each one of these situations, maybe I'll just put a dot beside them. We'll notice that acceleration and velocity are in the same direction. Okay, in each of those cases, our object would be getting faster. Okay, if acceleration and velocity are in opposite directions, then our object would be slowing down. Okay, I want to talk about and just formalize some problem-solving steps in physics. Number one is we're going to read the question, and I'm even going to put on here, let's do that a couple times because it's key that we're going to read and understand what's going on with a question. Okay, next, really big fan of diagrams. So we'll draw a picture. Okay, and we'll also indicate a positive direction. Positive direction. Okay, that's my short form for direction. Okay, step 3 in our problem-solving steps, I'd like to show our knowns and unknowns. What's given to us in the question, and what are we trying to find? Okay, step 4, let's state what equation we are going to use to solve the problem. Okay, step 5, I like to refer to as the plug and chug. Plug and chug. Plug numbers into a calculator, let's chug out an answer, and then step 6, of course, is state your answer. We'll do that with units and correct sig figs. Units and sig figs. Okay, and then I also love asking the question, hey, does that make sense? Or I'm going to even say, does my answer make sense? Makes sense. And off the hop, when we start plugging in numbers, maybe your answer, you won't be able to answer that. You won't know if your answer is making sense. But I hope over time we're going to build up some examples and some framework for what individual numbers mean when we are looking at solving some problems. Okay. So here are 4 examples on the back. We'll go through these fairly quickly. If we have example number 1, a sprinter starts from rest and reaches a speed of 12 meters per second in 4.25 seconds. Find their acceleration. So with this one, I'm just going to underline some key information. And along my left-hand side, I'm going to write out my knowns and unknowns. Okay, if a sprinter starts from rest, then their initial velocity would be 0. Their final velocity would be 12 meters per second. Okay, their time for doing that is 4.25 seconds. And then also, let's write down our unknown. I'm just going to put a question mark there. We don't know what our acceleration is. Okay, next I'm going to write out our formula for acceleration. Final velocity minus initial divided by a time of 4.25 seconds. Okay, and we'll find that our Velocity changes. Velocity in this case changes by 2.8235 meters per second every second. Okay, I'm going to go back and just look on the left-hand side at my knowns and unknowns and just have a think about sig figs. We're going to chop this to 2 sig figs because of our 12 meters per second given in the question. So we'll chop this to 2.8 meters per second squared is our acceleration. Put a box around that guy and it's done. Okay. Okay, next example, if we have a van that brakes from 50 kilometers an hour to 15 kilometers an hour in 4.6 seconds, what is its acceleration? Okay, my initial velocity is 50 kilometers per hour, and I'm going to right away, I'm going to change that to, just put a little divide by 3.6 here. I'm going to change that to meters per second, which is 13.8 repeated meters per second. Okay, the final velocity in this case would be 15 kilometers per hour. Okay, and we've all experienced this, pulling up to a stoplight or something makes us slow down. And we feel like we're getting pushed into our seatbelts. Okay, so our acceleration in this case, whatever our math works out, the question I'm going to ask at the end, does it make sense? Well, our number should definitely be negative because we're going to be slowing down. Okay, so here's all of our variables, our knowns and unknowns, and then if we go and plug these numbers into our formula, we should find that our final minus our initial velocity divided by our time, I think that works out to negative 2.113 meters per second squared. Okay, and then if we chop that to sig figs, there are 2 sig figs in the question, so we'll chop that to negative 2.1 meters per second squared. Checked it for sig figs, checked it for units, put a box around it. Okay, that guy's done. Okay. Okay, next up in example 3. Okay, this time we will solve for a different variable. So if we have a skier traveling at 4.5 meters per second, okay, how long will it take her? How long is asking us for time? So I'll just jot that down right now. How long will it take her to reach 21 meters per second? So that'll be our final velocity. If she can accelerate at a rate of 3.2 meters per second. Okay, so this is someone traveling down a hill. Our acceleration formula looks like so. Oh, and look, just out of habit, I've changed my VF to V2 and my VI, or my initial velocity, to V1. This is something that I will do interchangeably, and depending on the text that you are looking at, final velocity or V2, these mean the same thing. So we should just get used to using those interchangeably, just knowing that it's velocity of some final situation. Okay. Okay, next, if I want to solve for my variable of time, I'm going to multiply both sides by t and divide both sides by a. Okay, and that's going to help me get my time variable isolated. So time is going to be v2 minus v1 over a. Okay, and our plug and chug here is we put in 21 minus 4.5 divided by 3.2 seconds, or sorry, 3.2 meters per second squared. We find that our time, I'm just going to chop this straight to sig figs. Make sure you go through that calculation, please, and make sure we get the same numbers, but it should be about 5.2 seconds that it takes for this object or this skier to accelerate. Okay. Okay, last question. Is a ball dropping off a cliff? Okay, ball being dropped off a cliff. A ball being dropped off a cliff, that dropped word means that its initial velocity is 0 meters per second. Okay, what is the velocity after a certain amount of time? Okay, time is 2.1 seconds. Okay, and then the other thing that we know here is that our acceleration is always negative 9.8 meters per second squared downwards. And this, just a reminder, this is a constant. There are an infinite number of sig figs. So that number is not going to affect how we state our sig figs in our answer. Okay. So acceleration formula, we're going to solve this formula for VF. Okay, to do that, I'm going to multiply both sides by time, and I'm going to add VI to both sides as well. Okay, so my other side becomes VI plus A times T. And I show it like that because I think that's how it's shown on your one option on your formula sheet. Okay, so now if we plug and chug some numbers, we get 0 plus negative 9.8 times 2.1 seconds, or our VF is negative 21 meters per second once we chop it for sig figs. Okay, which makes sense. If we drop a ball off a cliff, okay, if we drop it and its initial velocity is 0, at some later time, the speed of this thing is going to be significantly faster than 0 because it's, we're dropping a ball, but it's also going to be acting in the negative direction, which makes sense. It's going to be acting downwards. So there are a few examples for how to solve some acceleration problems. We've got some practice to do on your worksheet, and then a little activity to do at home to find the acceleration of your car. Okay, thanks, folks, and we'll see you again soon.